Welcome to a video where we will introduce the idea of inverse functions. In this video, we will use Desmos to graph our functions and the inverse functions. Let's get started. All of the graphs used in this video are linked in the video description below. Please feel free to use the graphs to follow along with the video. In math, we are concerned with when we can undo a process. This is where the idea of an inverse function comes from. But before we get too far into the weeds about inverse functions, let's just think about when we undo or reverse a process. Consider how you drive from home to work. When you leave your house in the morning, you might turn left on one street, go north, and then turn right, maybe head east to get to work. Of course, I know I'm simplifying things here. Now consider when you're driving from work to home, you want to reverse the process. Where you drove east in the morning, you would drive west in the evening. Where you turned right in the morning, you might turn left. Where you drove north, you would drive south. Where you took a left turn, you might take a right turn. And while I'm probably simplifying the process of your drive from home to work and from work to home, all we're doing here is just reversing the process. And the key is that we end up back where we started. Let's start to build the concept of an inverse function in math. Informally, inverse functions undo each other. Let's take a look at a few examples. Consider the function f of x equals x plus 3 and g of x equals x minus 3. These two functions are inverses of each other. And if you think about it, the first function, f, is adding 3 to x, and g of x is subtracting 3. Addition and subtraction are usually known as opposite actions in math, but let's look how they reverse the process. Let's take a value for x, like let's say 5, and let's put it through our f function. F takes 5, adds 3, and we end up with 8. And now let's take that result and put it through our g function. So g would take 8 and subtract 3, and we end up back where we started at 5. So g reverses the process of what f did. G is undoing the effect of the function f. Here's a second example. F of x equals 2x, and g of x equals x divided by 2. Our first function multiplies x by 2, and the second function divides x by 2. And hopefully it should make sense that these are opposite actions. One's multiplying by 2. The opposite would be to divide by 2. It seems plausible that those could be inverse functions. But now let's put them through our conveyor belt. So let's take a starting point, say x is 6, but this time let's put it through the g function first. So g would take 6, divide it by 2, and we'd end up with 3. Now let's take that result of 3 and put it through our f function. F would take 3, multiply it by 2, and we'd end up with 6, right back where we started. This is a key when we're talking about inverse functions. They undo each other no matter which function comes first and second. If we take f and then apply g, or take g and then apply f, we end up back where we started because these functions undo each other. Now let's formalize the idea of an inverse function. Formally, if f is a function from set A to set B, then an inverse function for f is a function from B to A with the property that a round trip, in other words, function composition, from A to B to A, or from B to A to B, returns each element of the initial set to itself. Equivalently, we can also say that two functions f and g are inverses of each other if for every value of x, if we take f of g of x or g of f of x, we end up back where we started with x. A function f that has an inverse is called invertible. The inverse function is uniquely determined by f and is denoted by f raised to the -1 exponent, but that is read f inverse. You might be wondering, are all functions invertible? Sadly, no, not all functions are invertible. That usually brings up the next question: what types of functions are invertible? Only functions that are one-to-one are invertible. A one-to-one function is a function in which each input has one unique output. In other words, every y has exactly one corresponding x. Well, why does a function have to be one-to-one to be invertible? Well, we have to be able to reverse the process. Let's take a look at a process that's not one-to-one. Like maybe you have a traditional key to your house, and every person in the house has their own key to open the door. When several different keys can unlock the same door, there's no way to reverse the unlocking event to know which key was used. Because multiple inputs lead to the same outcome, the process cannot be undone. In contrast, a digital lock with a unique PIN allows each code to be matched to a specific unlocking event. Since every input produced its own distinct outcome, the process can be reversed, and we can determine exactly which code was used. So it's important for the process to be one-to-one so that when we reverse the process, we get exactly one thing back. Now let's take a look at a few graphs and determine which functions are invertible. The only types of functions that are invertible are functions that are one-to-one. Graphically, we use the horizontal line test to determine if a function is one-to-one. If all horizontal lines intersect the graph of a function and at most one point, the function is a one-to-one function, where you have one unique output for each input. If any horizontal line intersects the graph of a function at more than one point, the function fails the test and it is not a one-to-one function, which would mean that it would not be invertible. Let's take a look at these four graphs. And remember, these four graphs are linked in the video description. Let's draw some horizontal lines through the first graph. This first graph looks like a wave, and in fact, any horizontal line will touch the graph in more than one point. So this function is not one-to-one. If it's not one-to-one, then it is not invertible. Moving on to our second graph, if we draw horizontal lines through this graph, we can draw at least one in the middle of my picture where the horizontal line touches the graph in 3 different points. So this function is not one-to-one, and if it's not one-to-one, then it's not invertible. Moving on to our third picture, let's draw some horizontal lines to see what happens with this third function. Any horizontal line that I draw is going to touch this graph at most one time. So this function passes the horizontal line test. This function is one-to-one, so it is invertible. Now let's look at the fourth graph together. Let's draw horizontal lines through this function to determine if it's one-to-one. Any horizontal line that I draw is going to hit the graph at most one time. So this function also passes the horizontal line test, so it is one-to-one, which means that it is also an invertible function. Now that we know how to tell whether or not a function is one-to-one and therefore invertible, let's learn how to determine the inverse function. The first step is to determine if the function is one-to-one. Once you know that the function is one-to-one, you want to interchange or swap the x and y variables. The third step is to solve the new equation for y. This is your new inverse function. You'll replace y with f to the -1, which is red, f inverse, symbolizing the inverse function of f. These are the steps to determine the inverse function. Now let's work a few example problems. Let's determine the inverse function for f of x is equal to the points 1, 2, second point -2, 3, third point 5, -2. Our first step is we need to check to see if this function is 1 to 1. Let's try to visualize f by drawing a picture. So I have two circles here with the domain and range of f. So under our f function, we have the first point 1, 2. So this means 1 gets mapped to 2 under the f function. Our second point, negative 2, 3. Negative 2 gets mapped to the value 3. And our third point for this function, 5, negative 2, 5 is getting mapped to negative 2. So this function is definitely 1 to 1, and so it has an inverse. When we're looking for the inverse function, we need to swap the roles of x and y. You're reversing the process. Let's find f inverse now by reversing the process. So under the f function, 1 got mapped to 2. The inverse function reverses that. So 2 goes back to 1. In the original function, negative 2 got mapped to 3. The inverse function would reverse that. So 3 goes back to negative 2. And finally, our last one was that 5 got mapped to negative 2. Reverse that. Negative 2 goes back to 5. So in an inverse function, the roles of x and y are swapping. One thing that also happens is what was our range for the f function now becomes the domain of f inverse, and what was our original domain for f is now our range for the inverse function. And this is a key point of all inverse functions. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. And if you think about it, that's because the roles of x and y are swapping. What was the domain of f, the x values, becomes the range of f inverse. What was the range of f, or the y values, now becomes the domain of f inverse. Now let's take a look at a different example where we're given a formula for the function. So let's determine the inverse function of f of x equals x cubed plus 2. Let's remind ourselves of the steps used to determine an inverse function. The first thing that we need to do is to determine if the function is 1 to 1. So let's take our function over to Desmos, graph it, and use the horizontal line test to determine if it's 1 to 1. Open your browser to desmos.com. You can either click on the button to open the graphing calculator or go up to the Math Tools menu and select Graphing Calculator. When the calculator opens, you should be looking at a blank graph. Let's go over to the left-hand side and enter our function. F of x is equal to x cubed plus 2. I'm just going to increase the thickness of our function so it's easier to see. If we draw horizontal lines through this function, we would see that every horizontal line touches the graph at most one time. So this function passes the horizontal line test. That means that it is 1 to 1, and since it's 1 to 1, this function is invertible. So step 1 passes. The function is 1 to 1. The second step is to interchange or swap the x and y variables. Well, our function f of x does not explicitly have a y variable, but f of x and y are interchangeable. So let's replace f of x with y, and so we would end up with y equals x cubed plus 2. And now let's interchange or swap x and y. So if I swap x and y in the formula, I would end up with x equals y cubed plus 2. Now we need to solve this new equation for y. So my goal is to isolate y by itself. To do this, I need to start by subtracting 2 to the right side. Of course, what I do to the right side, I need to do to the left. This would leave us with x minus 2 is equal to y cubed. I'm trying to isolate y, so I need to undo y cubed. To undo the y cube, I will need to cube root both sides of the equation. Cube root of y cubed is just going to give me y on the right-hand side. So this leaves me with cube root of the quantity x minus 2 is equal to y. And the fourth step is to replace y with f to the negative 1, symbolizing the inverse function of f. So f inverse of x is equal to the cube root of the quantity x plus 2. Let's go back to Desmos and let's add this inverse function, cube root of the quantity x minus 2, to our graph to see the relationship between a function and its inverse. Let's go over to the left-hand side and add our inverse function. Unfortunately, Desmos doesn't like me to call it f inverse of x, so I'll just call the inverse function g of x. If you need to type a cube root or any type of root into the Desmos graphing calculator, click on Show Keypad toward the lower left-hand side of the screen, and then click on Functions. Scroll down until you find the nth root. Now you'll be able to write cube root of x minus 2. Once again, I'm going to make this graph a little bit thicker for us. Hopefully it's clear that these graphs are in fact related. In fact, they almost look like mirror images of each other. And that's not a coincidence, actually. These graphs are mirror images across the diagonal line of the plane. So let me add a line to our graph. I'm going to add the line y equals x. And I'm just going to change the color of it to be green. This line here is the diagonal line of the plane y equals x. And what happens with inverse functions is that they are mirror images across this diagonal line. This is always a good way to check to see if you did in fact find the correct inverse function. If you graph a function and its inverse, they should be mirror images across the diagonal line y equals x. To summarize that last point, the graphs of inverse functions are always reflections of each other across the diagonal line y equals x. This is a property of every single function and its inverse. So if you draw two functions and they are not mirror images across the diagonal, then they are not inverse functions. Let's take a look at one last example. In this case, our function is h of x equals 2 divided by the quantity x minus 3. If we want to determine the inverse function, our first step is to ensure that this function is 1-to-1. Let's go back to Desmos to see if it's 1-to-1. I'm just going to edit the graphs of f and g. So I'm going to delete g of x, and I'll delete f of x and replace that with h of x. H of x equals 2 divided by x minus 3. The first thing I'm going to do is I'm going to make the function a little bit thicker so it'll be easier to see. Now the next thing I need to do is to go over to the upper right hand side, and to make the window a little bit larger, I'm going to edit the x and y axis to be from -10 to 10 for both x and y. Here's our function h of x. It looks like it would pass the horizontal line test. Any horizontal line that we draw would touch the graph at most once. So this function is 1-to-1, and therefore it is invertible. Okay, so we know h of x is invertible because it is 1-to-1. The second step is to swap x and y. Well, y is not explicitly written here, but h of x and y are equivalent. So let's replace h of x with y. I would have y equals 2 divided by x minus 3. Now let's do the second step. Let's swap x and y in the functions. So I would have x equals 2 divided by the quantity y minus 3. And now our goal is to solve this function for y. The first thing I want to do is to clear the fractions. So let's multiply both sides of the equation by the quantity y minus 3. This will clear the fraction y minus 3. Let me move over to the upper right-hand side here. Now I have the quantity y minus 3 times x is equal to 2. Keep in mind that we're still trying to solve this equation for y. I'm going to need to distribute x into the parentheses. That would give me x times y minus 3 times x is equal to 2. We're trying to solve for y. So the next thing we need to do to get y by itself is to add 3x to that left-hand side. And of course, what we do to one side, we have to do to the other. So this would leave us with the quantity x times y is equal to 2 plus 3x. Currently, y is being multiplied by x. So if I want to get y by itself, I need to divide by x. What I do to one side, I need to do to the other. So I'm going to divide both sides by x. These will cancel the x's on the left-hand side. This leaves us with y equals the quantity 2 plus 3x divided by x. This cannot be simplified, so this is our inverse function. Let's call it h inverse of x is equal to the quantity 2 plus 3x divided by x. Now let's just check to make sure that this is in fact our inverse function by going back over to Desmos, adding this inverse function to the graph, and making sure that h of x and h inverse of x are mirror images across the diagonal line y equals x. Just as with our last example, Desmos doesn't like the notation h inverse of x, so I'm just going to call the function g of x, and that was equal to the quantity 2 plus 3x divided by x. And let's make that a little bit thicker so it's easier to see. I'm going to add the diagonal y equals x to our graph, and these in fact do look like mirror images across that diagonal. So this is a good way to check, hey, we did find the correct inverse function. So since we graphed h of x equals 2 divided by the quantity x minus 3, and h inverse of x equals the quantity 2 plus 3x divided by x on our graph, this in fact ensures us that our functions are inverses since they are mirror images across that diagonal. Let's summarize. If a function f is 1-to-1, then f has an inverse function, f inverse. We use the horizontal line test to see if a function is 1-to-1. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. The roles of x and y swap or reverse for a function and its inverse. And finally, the graphs of f and f inverse are reflections of each other across the diagonal line y equals x. That's it for this video. Thanks for watching.